All right. Oh, okay. So, ladies and gentlemen, so we did, let's do a quick review. Let's shrug off the cobwebs. We did parallel circuits. We have series circuits. In a series loop, what is the same in every element in a series loop?
Current.
Current is the same in every element in a series loop because the charges can't pile up. The charges can only go as fast as the slowest element. So if you have one loop, all the charges are going the same speed. Like if you had one lane of traffic and everybody's obeying the law, everybody's traveling at the same speed. Okay? So it is current that is the same everywhere in a series loop. In a parallel section, or a parallel circuit, each branch has the same what? Each branch has the same voltage. In a parallel circuit, each branch has the same access to the battery. If you were not here for the parallel circuit presentation, please get on YouTube and watch it. It's really important. Although you'll probably pick it up pretty fast, but still take a look at it. So voltage is the same in each branch. Voltage is the same going into each branch in a parallel section because each branch has the same access to the battery. In a series section, it is each element in the same loop has the same current. Now, in a combination circuit, which is what most circuits you will encounter are, in a combination circuit, we have some strategies. It is both has series sections and parallel sections. So what we're going to do is we're going to try to reduce the parallel sections to make them simpler. Okay? This is the sequence we're going to use. We're going to calculate the equivalent resistance of any parallel section. Then we're going to draw a new circuit diagram reducing all the parallel sections to series sections. And we're going to solve it like a simple series circuit. And again, our VERP charts are going to work pretty well. This is the circuit we're going to use. 60 volt circuit. You don't need to write that down. We're going to show you another one in a second. We're going to blow it up. So we're going to use a VERP chart again. We got our battery. We're going to say R1, R2, and R3. And we're going to write P, I, R, and P. VERP. I need a new black pen. Four more weeks of writing. Okay, are you ready to jump in, or are you writing all the rules down? Again, we're going to do this so often you're not going to be able to forget it. So if you're a little concerned about reducing or writing all the rules down, I'm not going to worry too much about it because we're going to do this. Can we move on? Okay. So here's the circuit that we're going to work with. In this circuit, there's a 60 volt battery. R1 is 8 ohms, R2 is 30 ohms, and R3 is 20 ohms. So this is a combination circuit because there's a parallel section and a series section. Oh, quick review. Which side is the high potential? Is it the top or the bottom that's the high potential? Top is the high potential. Long bar is high potential, short bar is the low potential. In what direction is the conventional current going? Is it going clockwise or counterclockwise? Clockwise. Yeah. So the conventional current, which is positive, is going clockwise, and the electrons are going the opposite direction, counterclockwise. Okay. So quick review of current. The current travels from high potential to low potential, so it travels clockwise in this case. Electrons are the opposite. Electrons travel from low potential to high potential because they're negative, so they travel counterclockwise. Are we cool with that? Okay. So let's make our VERP chart. So V, I, R, and P, battery R1, R2, R3, and then write down the items that we already know. So go ahead and make your VERP chart and write down the items that you already know from the circuit. R1 is 8 ohms. Sorry, it's kind of, yeah. So R1 is 8 ohms. R2 is 30 ohms. And then R3 is 20 ohms?
Yeah.
And we also know that the battery is 60 volts. I think that is the limit of everything we already know. Okay, so now if you looked at this and you didn't realize this was a combination circuit, you could be like, oh, I know what the battery is because I can put them all together. The problem is you can't just add them up together like they were a series circuit, and you can't use their reciprocals like they're a parallel circuit because it is a combination circuit. So what we're going to do is we're going to collapse R2 and R3 into a virtual resistor. Okay? A resistor that doesn't really exist but helps us do the math. Okay? So we're going to collapse R2 and R3 into a virtual resistor, and R2 and R3 are a parallel section. So what do we do with parallels? Reciprocal. So I'm going to make a box. I'm going to make a box between R2 and R3, and that's going to represent my parallel section compressed into a virtual resistor. So again, we're going to take the equivalent resistance of R2 and R3, and we're going to compress the parallel section into a single virtual resistor that doesn't exist, but makes our math work. And again, quick review, in a series section, the equivalent resistance will always be larger than the largest resistor, but in a parallel section, the equivalent resistance will always be smaller than the smallest resistor. So you're looking for an equivalent resistance that's less than 20. Oh, so for parallel, the equivalent resistance RP is 1 over RP is 1 over R1 plus 1 over R2 plus 1 over R3 and so on.
Wait, I'm confused. Would an equivalent resistance say that they're the same? So why would it be less?
When we say equivalent resistance, we mean equivalent to the section that we're looking at. So you take the 20 and the 30, the equivalent resistance going into the 20 and 30, that's what the battery would see, or that's what the single road would see before it branches into 2 roads. So if you compress a 20 to 30, the two together would have an equivalent resistance of 1 over 20 plus 1 over 30. Does that make sense? That number is simple. So what did you get for the equivalent resistance for that section? 12. So the virtual resistor, the equivalent of 30 to 20, gives you a 12 ohm resistor. And we can rewrite the circuit for the resistor, and we're going to call it R23. So R23 has, this is R23 has an equivalent resistance of 12 ohms. And now we have a series circuit. Yay! Yes?
I'm so confused about 12.
Okay, so the 12 came from, we're looking for 1 over RP, so 1 over 20 plus 1 over 30. So I did 1 divided by 20 plus 1 divided by 30, enter, and then 1 over answer or reciprocal answer.
Oh.
Yeah, this is the hardest part about doing circuits, is in the heat of battle you forget to take the reciprocal. That's why you need to remember, and always check yourself. Equivalent resistance, a series circuit will always be larger than the smallest, but larger than the biggest resistor. In parallel, it'll always be smaller than the smallest resistor. Okay, so are you with me right here? Give me a thumbs up if you're with me right here. So far, so good. Now, we've reduced this into a series circuit, making it very, very easy. So now we can find the equivalent resistance of the battery. 20, yeah. Because the equivalent resistance at the battery is going to be the 8 plus the 12, or 20 ohms. So it's going to be the 8 real resistor plus the 12 virtual resistors.
And sorry,
That's okay.
it's like
if the charge has a choice, it's a parallel circuit. So the charge goes through the battery, or leaves the battery, goes through R1, and now has a choice between R2 and R3. So a parallel circuit is a branch. Kind of like if you're driving in a one-lane freeway, and all of a sudden it splits to two, you have the choice. Do I go left, or do I go right? Parallel. Okay. So the battery is going to see 20 ohms of resistance. The battery has no idea what's going on. It doesn't know that there's a 30 here and a 20 here. It can basically just assume it's a 12. The battery only sees what comes out. Okay. So we have an 8 ohm resistor and a 12 ohm resistor. Those two together make 20 ohms of resistance. Okay. Give me a thumbs up if you're with me so far. Now that we know that, we can basically find circuit current. What's my circuit current? 3 amps. So I've got 3 amps coming out of the battery. Where else? 3 amps in R1 as well. And in the virtual resistor also sees 3 amps. The virtual resistor also sees 3 amps because R12 or R23, the 12 ohm, is in series with R1. How are we doing? Okay. Yay, we got this. Okay, now we have some options. We got lots of options. We can basically say, oh, I know what the voltage going through R1 is, and we can solve for that. Or we could say, I know the voltage going through the virtual resistor, and we can solve for that. So let's do both. So let's build our virtual resistor, and let's use V equals IR to figure out what the virtual resistor voltage is. I'm sorry? Did you answer it?
Yeah.
Okay, so I got these little flaps. Okay, so yeah, 36 volts. So the virtual resistor gets 36 volts because you just did the V equals IR. Also, again, you can go this way or you can go this way. R1 would get how many volts? 24 volts. How convenient is that? Does 24 plus 36 equal 60?
Yeah.
Yay, we're on the right track. Now, what do we, we're going to have to do something here. And we're going to have to realize that in a parallel section, what is the same in each branch of a parallel section? Voltage. Each branch of a parallel section, it is the voltage that is the same. So, if there's 36 volts, listen carefully, if there's 36 volts in the virtual resistor, that means the real resistor that make it up also gets 36 volts. Just a second.
Oh, yeah. Where I'm a little confused because the virtual resistor on the others aren't the same values. So why would it be the same value?
Because the virtual resistor represents a parallel section. And in a parallel section, each branch gets the same voltage. So this virtual resistor represents R2 and R3. So if you know the voltage of the virtual resistor, R23, that means R23 really is R2 and R3. So if the voltage of R23 is 24 or 36, that means R2 is 36 and R3 is also 36. Because every branch in a parallel circuit gets the same voltage. Yes?
Why does it say 12 ohms by R2?
Because it's a virtual resistor. So 20 and 30 compressed into a virtual resistor is 12 ohms.
Oh, I was looking, on my chart I was looking at like the bottom. I was like, that's 20. Why?
This is probably one of the most complicated part of combination circuits, is realizing that you have to apply the rules to virtual resistors. The virtual resistor in this case represents two parallel branches. If the virtual resistor is getting 36, then that means each of those branches gets 36.
So does a virtual resistor make the parallel like a series for the
Yep,
purposes of the chart?
that's exactly what it does. It allows us to reduce convoluted parallel sections into series sections. And in this case, there's only one parallel section. Sometimes you get circuits that have multiple parallel sections and you compress them multiple times. But in this case, there's just the one. So, yeah.
There's one, but there's two.
One parallel section that gets reduced into one virtual resistor. But the rules don't change if it becomes more complex. If we have a whole bunch of parallel sections, you just reduce those parallel sections into series resistors. Cool? Okay. Let's finish up. 36 divided by 30 is going to give you the current. 36 divided by 20 is giving you the current. You want to go ahead and do those? 1.2?
And then 1.8.
1.2 amps and 1.8 amps. And again, in a series section, in a series section, it is voltage the same, but these are a parallel section. In parallel, you add the currents and it becomes 3 amps. If you have 3 amps going down one road, and that one road splits into 2 roads, 1.2 and 1.8. 3 in, 1.2, 1.8. Back to 3, back. Hey look, we're done. So let's calculate power and see how we did. Let's calculate the power of all the devices. Once again, power is current times voltage, P equals IV. So let's calculate power to check our work. We always check our work. That's why it's verb and not verb. You can even call it verpiv if you want. Verpiv! But no. Verpiv. Did we do it right? How do you know if you did it right? Power is energy divided by time. If whatever power is coming out of the battery equals the power to each item, then you did it right. Okay? So whatever the battery produces has to be dissipated in each of the items. Yes?
And then the one you get for the virtual resistors should add up to R2 and R3 individually, right?
For power?
Yeah.
We don't care.
Okay, but
Yeah,
show
the virtual resistor doesn't actually exist, so you don't use a virtual resistor for power.
So you don't have to find the power of the virtual
No.
resistor? Okay.
In fact, I recommend you don't. Yeah. That's a very good question. I'm glad you mentioned that because I forgot. Don't find the power of the virtual resistor. You don't need it. It's just going to confuse you because it doesn't really exist. It doesn't really dissipate any kind of energy, so we don't care about it. So how much juice does the battery put out?
180.
180 watts? How much juice does R1 consume?
72.
72 watts. How much juice does R2 consume?
40.2 watts.
You said 23.2?
43.
43.2 watts. And how much juice does R3 consume?
64.8.
64.8 watts. And the 64.8 plus 43.2 plus 72.180?
Yes.
Yay! And once again, for the purposes of practical use, this means the following. 1. Every second, this one's pumping out 180 joules per second, 72 joules per second, 43.2 joules per second, and 64.8 joules per second. Which means, if these were light bulbs, which one's the brightest? Brightest. If these were light bulbs, this one's the brightest because it's pumping out 72 joules per second. If these were light bulbs, this one's the brightest. If they were horns, this one's the loudest. If they were motors, this one's the fastest.
Yes. Does that mean that resistor is the weakest?
No, it just means when you find the power, depending what the resistor represents, that's going to be the most energetic. So if these were all light bulbs, this one would be the brightest light bulb. because it's pumping out 72 joules per second. If they were motors, this one would be the fastest. If they were horns, this one's going to be the loudest. If they were, what else can we do? If they were chemical reaction catalysts, this one would be the best. That's what it is. Give me thumbs up, you're ready to do one more practice. All right. All right. Go ahead and copy this verb chart. You might have noticed something kind of weird about this. Go ahead and copy this circuit and make the verb chart. This is about as exotic as things get. If you can handle this today, then you're going to be in great shape. If you can't, you'll still be in great shape. You'll have to figure it out over this week. Once you've got your verb chart, fill in the information that's already given to you. Again, if you want colored pencils, you can help yourself to colored pencils. I like to use different colors for different things, but that's just me. So what do you notice that's kind of weird about this circuit? Yeah, it's got an ammeter in it, and it doesn't tell us the voltage at the battery, which is weird. So every now and then you can be like, oh, don't panic. Okay, don't panic. Every now and then you get a weird one like this. They're like, but it doesn't give me the voltage at the battery. What do we do? We'll figure it out. Figure it out. In this case, it gives us the current through R4, which is 0.00525 amps. So it gives us the current through one of the branches, which, believe it or not, is actually extremely useful. Do a little circuit jitsu on this, and yeah, you can totally do this. Give me a thumbs up, you're ready to move on. You've got your verb chart good to go. You're ready to break into this thing. It's like almost everybody. All right. So what box is jumping out at you right now that needs to be taken care of?
R4 voltage.
R4 voltage, yeah. So you've got I and R, why not find V? So let's find R4's voltage. 3.54? All right. I am going to use 3 significant digits, and that's just going to be easy, so
544.
3.544?
Yeah.
Okay, just go 3.54 volts. It's 3 significant digits. I realize you guys don't learn significant digits anymore. Think about basically, like, how do I teach you significant digits? How do we go? It's very, very difficult. All right, boom. How cool is this? Now, this is the voltage through